Today we're going to be looking at momentum, and more specifically how we can relate it to force, and to how we can relate it to an orbit. So this simulation right here in VPython that we're looking at right now shows us essentially a spacecraft that we're going to try to get to orbit the Earth. So we're given a couple of constants like the mass of the Earth and the mass of the craft and gravity and so on and so forth. But what I'm really interested in is these two things right here. Because what this one means right here is we're given a velocity, which is a vector quantity. So straight up and down in the y direction, we can see this 2750. This 2750 just means that there's 2,750 meters per second going straight up in the air. That's the initial velocity that our craft is going to have. And our initial momentum, which momentum is just equal to mass times velocity, is going to be equal to the mass of the craft times this initial velocity, and that gives us our initial momentum. So as we go down here, we get into the while loop, which just kind of repeats these calculations over and over again until we end up through our sim time, which is about 4 days is what we're looking at. So the first thing that we need to do right here is update the craft's momentum. So we have delta P equals F net delta T. And essentially what that is that's just the momentum principle. The change in momentum is equal to the net force times the delta, or times the time over which it's applied. That's pretty basic. That's pretty easy to understand. But what is this F net C? What is this? This is the net force on the craft. How do we get that? Well, we have to go up here and look at this. Since Earth is the only object that's interacting with our spacecraft, and it's doing that through gravity, we know that the magnitude of our force is just going to be equal to big G, which is a constant, times the mass of the Earth times the mass of the craft, divided by the distance between them squared, which is just what this R mag is. Then down here we look and we say this F net C is equal to FCE, which is what we've given up here just in magnitude form. So now we know our F net and we know our delta T, so we can find our delta P. However, in order to update it, we don't want the change momentum, we want the new momentum. So we have our delta P down here, but we also want to add that to the craft.P, which is what we calculated up here initially. Now that gives us a new craft.P. We can do the same kind of thing with the position delta R, which is a change in position. That's just equal to velocity times time. Well, since momentum is equal to mass times velocity, and we have a momentum and we have a mass, then we can just divide the two and then get the new momentum as this delta P change, or as this craft.P changes. And then we do the same kind of thing where we start with our original position of the craft and add it to delta R, which is what we calculated up here to get the new position. So if we do this, and we have our initial velocity of 2750, excuse me, and we run this module, then we're going to see that this craft has this initial momentum all the way up here, and it's going to bend around the Earth in a nearly circular fashion, kind of a circular fashion. It's a little bit. Actually, it's pretty oblong, but that's all right. That's all right. We can deal with that. But we do have our momentum. Or we do have our orbit, I should say. So as this momentum is, as the position of the craft is changing, then we see that the momentum is also changing direction-wise, but magnitude, this arrow always stayed the same. So that's good. That's exactly what we wanted. So we can play around with this if we want, but right now I'm running out of time. So for now, I'm going to leave you there. Thanks.